Bon, bonjour à tous, bienvenue pour cette nouvelle année, joyeuse et belle année à vous tous. Aujourd'hui, on a le plaisir d'accueillir Anne-Laure Dalibard. Donc, Anne-Laure est professeure au laboratoire Jacques-Louis. Elle fait des mathématiques et elle va nous faire des mathématiques au tableau. Donc, un bon début d'année avec des maths au tableau. Et puis, je ne vais pas en dire beaucoup plus, mais je vais laisser Anne-Laure présenter son travail et puis le sujet du jour.
Merci beaucoup. So I will talk in English. And so first, Happy New Year to everybody and many thanks for the invitation. So as Stefan mentioned, I'm a mathematician, and more specifically, I work in the theoretical analysis of PDEs. So I don't do numerics. I really do only theory, with pen and paper. And for the last 10 years, I've been interested in fluid boundary layers, so in the mathematical analysis of fluid boundary layers. And so I have to say that I'm a bit intimidated because when you work in the PD analysis of fluid mechanics and you give it in a fluid mechanics lab, you always have the feeling or the fear that everything that you're going to explain is already well known by the whole community. Okay, so this is clearly one of my fears. So please interrupt me if I know that many things that I will say today are well known by all of you, but please don't hesitate to interrupt me if I can speed up. And as I mentioned to Stefan, so I like giving Blackboard talks, which is typically a mathematical a habit in the mathematical community, because it allows me both to not to go too fast and also to adapt a little the talk as it goes. So if you want me to slow things down or to speed up, please say so. And if you have any type of questions, again, please interrupt me. Okay. And before I start, let me also mention that this is so I will present today a rather recent result that I obtained with two of my collaborators, one which is my former PhD student and another one who is a former postdoc of mine and who is now a researcher in CNRS. And it's a subject on which we had been working for a while and which concerns recirculation phenomena typically in the Prandtl boundary layer. And it took us a while to complete our proof because we didn't expect what we found. Okay, so at first we tried to prove something that was actually false, as I will try to explain. So this was a bit of a surprise. And so that's one of the reasons why it took us so long. And okay, so we found some things that were rather unexpected. So if you tell me that you all know this by heart, okay, be maybe a bit sad. But then I have questions for you because in the end, okay, I'm satisfied with the mathematical result that we have, but I think that it's not a very physical result, and I think that maybe I should modify the problem that I'm looking at in order that it makes more sense from a physical point of view. And this is where I would like to have your input. Okay, so now, so the title of the talk that I gave was Recirculation and Singularities. And also, so I think that the talk is also online. If I should write larger or something, yes, yeah, please tell me. Okay, so that's the title that I gave, and so I will start with a small introduction on recirculation, but this is the part that I guess you all know very well. Okay, so let's say that you're looking at a fluid boundary layer in which you have an adverse pressure gradient. Okay, so if you look at a cross-section of the boundary layer as you move, so here you have your solid wall, okay, and you look at different abscissa along the wall. So say at first, when you are at the far left, you will have something that will say looks like a bit like the Blasius solution, something like that. Okay, and then because of your adverse pressure gradient, when you move along the wall, you will have something that is steeper, right? So I will try to draw something a bit steeper, maybe something like that. And then at some point, you reach a point where you have some boundary layer separation. So your flow will look like something like this. Okay, so this is the separation point. And then when you move further along, what you have is a recirculation bubble. Okay, so here, so this is my velocity u, and here you have a zone in which u is negative, and here u is positive. Okay, so here you have recirculation. Right. So from the, let's say, again, I will focus on the mathematical results. So in the PD analysis community, these regimes before separation have been studied in the 70s by Oleinik and her collaborators. So this is a theory that was rather well known because in that case, the stationary Prandtl equation looks like a parabolic equation, so like the heat equation, if you want. Okay, so in that case, you have let's say, a well-identified, well-posed nest theory. Okay. Then, when you reach separation, so you will have the Goldstein singularity, and this is something that we studied with one of my collaborators, Nader Masmoudi, a couple of years ago. And then the last thing that remained to study, at least as long as you focus on the Prandtl equations, okay, I won't be talking in this talk about, say, the triple deck system or other boundary layer systems such as this one. I will focus on Prandtl and associated toy models. So these zones in which you had some recirculation, these hadn't been at all studied from the mathematical point of view. So it's really something that just happened in the last year. Okay, and so this is what I wanted to focus on. So if you focus on recirculation, the typical picture that we have in mind is something like that. So we look at a slice along the solid wall. Okay, so this will be x, and I look at a slice, say between x0 and x1. Okay, so I'm putting, say, some imaginary boundaries here at x0 and x1. And let's say that I'm looking at a given solution of the Prandtl system, which I know has a recirculation bubble. So typically, the Faulkner scan flow. Okay, so you look at the Faulkner scan flow, and so here the Faulkner scan flow has a looks like this. Maybe I would just lower a little this line. So you'll have something that looks a bit like this. So this will be a reference solution. So here you have u equals 0. Here you have u negative, and here you have u positive. Okay, and so again, this solution is well known. You don't have an analytic formula, but still you can study it numerically. You know a lot of properties and so on. And when you have such a specific solution at least in the PDE community, a natural question is whether or not you can perturb it. Okay, so can you look at solutions in the vicinity of this specific one? Okay, can you prove that there exist solutions and that they are unique in the vicinity of this recirculating solution? And so how do you do that? Well, you perturb a little the data. So in that case, the data will be the source term, meaning the pressure gradients, say, or you can perturb as well what happens on the boundary. Okay, and so when you want to perturb the boundary data, you need to be a bit careful. So now I'll write the equation, maybe. So the Prandtl equation in the stationary regime. So as you know, it looks like this. So you have u ux plus v uy minus u y, so this is x and this is y, equals a source term, which is minus dp minus the Euler pressure gradient on the boundary. Okay, and you have an incompressibility condition. Everyone is 0 on the boundary. And as you go to infinity, you go towards the solution of Euler. Okay? Okay, so this is your Prandtl system. Okay? So again, what Oleinik found and what you can easily convince yourself of is that when u is positive, so this term is just a transport term, and this is like a parabolic equation. Okay? So what you expect is that you will have an equation that is forward parabolic in this zone and backward parabolic in the upper, not half plane, but in the lower region. Okay? And if you believe that, then it's natural to enforce some boundary data here, okay, and here, right? Because this will be your initial condition, say, for this forward parabolic zone, and this will be your final condition for this backward parabolic zone. Okay? So in the rest of the talk, I will denote by sigma naught the zone on x equal x naught where u is positive. So this is sigma naught. And by sigma 1, the zone on x equals x1 where u is negative. Okay? Okay, so again, let's assume that I have a solution of Faulkner scan. Let me denote this by f. Okay, this is just my source term. Let's assume that I have my solution of Faulkner scan, and now I want to perturb f a little bit and perturb the boundary data on sigma naught and sigma 1 and try to see whether or not I can find a solution. Okay, so you have a solution UFS of Prandtl with a source or a pressure gradient. Pressure gradient F Faulkner scan. Okay, and you want to the goal is to construct a solution with a source term f, which will be your Faulkner scan source, plus a small perturbation. Okay, and boundary data. So it will be u on sigma I. This will be the value of UFS on sigma I, plus, again, a small perturbation that I will call delta I. Okay, that's the idea. That's true. Okay, the thing is, so you can choose, let's say that you choose the delta I, so that you do not move the extremes of the line here. Okay, so you assume that they vanish at that point and that point. You choose them very specifically so that they vanish, and so that you don't move the endpoints. It's not that important, actually. I think you can choose them so that you can actually move the endpoint, but it simplifies a little the technicalities if you choose them so that the endpoints of this line are not modified. Okay? Okay, so I choose the delta I so that the sigma I don't change, let's say. Okay, but again, this is not so important. It just simplifies a little the statement. Okay, so that's the overall setting. And the let's say the common belief when you look at that from a theoretical PDE perspective is that if you add here a perturbation delta F and some delta I's that are small, that are very smooth, and so on, then everything will go well, and you'll be able to construct a nice solution in the vicinity of this Faulkner-Scan flow. Okay, so the hope is that if you take a nice enough perturbation, a nice enough meaning, okay, again, very smooth. So Pierre told me don't go into Sobolev spaces, and I won't. Okay, but because here it's not my. I'll try to explain that it's really. It's not really a matter of regularity of the source of the perturbation. Okay, so you can think of perturbations that are C-infinity, compactly supported, the nicest perturbations that you can think of, anything. Okay, so again, this is not my point of view here. And so you hope that for such nice perturbations, you'll be able to construct a nice solution of your PDE. Okay? And our surprise is that this turns out to be false. Okay? Generically, you cannot do that. And you cannot do that, and here, this is the question that I will have in the end for you. I think my belief now is that this condition is not the correct one, okay? That you shouldn't do that. You should replace that condition with something that is maybe more like a transparent boundary condition, something like that, I don't know. But it turns out that when you take this type of problem, generically, you cannot build a smooth solution of this equation. And the solution that you build has some rather strong singularities in the vicinity of this point and in the vicinity of that one. Okay? So that's what I will explain in the rest of the talk. So maybe before going on, so this is a joint work with, I mentioned it, but I'll write it, with Frédéric Marbach, who is now in CNRS in INS Rennes, and with Jean Rax, who is a former PhD student of mine and who's now a professor in class préparatoire. And actually, in what we didn't study the Prandtl equation, but we studied a variant, which is a Burgers-like equation, in which we dropped this term. Okay, because it simplifies the analysis. Okay, it removes some a lot of difficulties associated with Prandtl. So the fact that it's a non-local equation, because in order to express V, you integrate this divergence-free condition, and so you have this introduces some non-locality in the equation and so on. So studying Prandtl introduces several additional difficulties. But everything that I will be saying today is true for Prandtl. Okay, it has been extended recently by Samir Ayer and Nader Masmoudi. So everything that I will be saying about the Burger system has been extended to Prandtl. So it's not specific to the toy model that I will be considering. Okay, but I'll be considering exactly the same. So the same equation, except that I don't have this term, and of course I don't have the divergence-free condition. Okay. Okay, so the equation I will be studying, maybe I'll write it here so that you have it, is ux minus uyy equals f. And also to simplify a little further, so you can construct the analog of the Faulkner-Scan solutions for this equation. Okay, you have a kind of ODE and so on, so this is manageable. But actually, for everything I will be saying, it's easier to try and construct solutions in the vicinity of a shear flow. Okay, so I will look at U, which is a perturbation of a shear flow, so Y plus a small perturbation. Okay. And so, of course, if you look at just the shear flow, so if you take u equal y, then this satisfies the equation with f equals 0. Okay, uyy is 0, ux is 0. So this is a trivial solution of the equation with f equals 0. So this is why this is a nice solution. And again, it's not, what I will be saying is not really specific to the Faulkner scan flow. The only important thing is that close to this line of changing sign of u, you change sign linearly. Okay, your uy is positive. Okay, you don't have it's not degenerate if you want. Okay, so again, if you once you are convinced that this is the important feature of the underlying solution, then you might as well study it with a very simple flow, which is just the shear flow. Okay, so yes, so I'll be studying this just to simplify things. And the last simplification is that actually, when you want to look at what happens in the vicinity of the recirculation line, you don't care about what happens at infinity. Okay, what happens at infinity doesn't really matter, and so you can somehow truncate your domain and work in a bounded domain in the vertical direction. So actually, my domain, which I will call omega, will be x0, x1 cross -1, 1. Okay, I shifted it a bit so it started at -1 instead of 0. Otherwise, it's not shouldn't be y, but it should be y -1. Okay, just again to simplify stuff. But the important feature here is that it's bounded. But again, this is just to simplify my own personal life. Okay, because it's technical enough as it is. Okay, and then in that case, the sigma naught, this will just be x0 cross 0, 1. And this one will just be x1 cross -1, 0. Okay. So this is but otherwise the setting of the problem is the same. Okay, so this is what I will be studying, and so maybe I'll start by stating the theorem that we have, and then I'll explain. I'll explain a bit where the difficulties that we encounter. So the theorem that we proved is the following. So you take f, delta naught, and delta 1 to be small and smooth. So I told you I don't really care about their regularity. You can assume that they are infinity with compact support. I don't care. Okay, and you can and the same thing for the smallness. You can take smallness in a say you control a very large number of derivatives, and you assume that the norms of the derivative are small. This is not relevant for what I will be talking about. And the thing is that there exists a smooth solution. And okay, so this part is important, and I will try to make it precise a little bit more later on. A smooth solution of my toy model. So the toy model is this one. If and only if f, delta naught, and delta 1 satisfy some orthogonality conditions. So what does that mean? That means that typically you want conditions like this. You want that the scalar product of f with some given profile, which I will call say theta k, plus delta naught on sigma naught times gamma k, plus delta 1 on sigma 1 times gamma 1k equals 0. Okay, and here you notice that there is an index k, And here I have to explain a little bit. So actually, when I say smooth, here the number of orthogonality conditions will depend on the type of smoothness that you want to have for your solution. Let me explain. If you want to control one derivative in x, then you will need two boundary conditions. And typically, this is what we have. So so you have two orthogonality conditions. Per derivative in x. Okay. So in what we did, we just wanted to control one derivative in x, and so we just had two boundary conditions. So here k is equals 0 and 1, say, so we have two of them. But if you wanted to control 4 derivatives in x, say, you would need 8 orthogonality conditions. If you want to control 100, you have 200 orthogonality conditions, and so on. Okay. So really, these conditions have nothing to do whatsoever with the smoothness of f or with its cancellation on the boundaries. It's really, you have to look at some integral and to look whether or not it's 0. Okay. And the difficulty is that, so a remark. Actually, I wrote them like this, but it's a bit misleading because the theta k, gamma naught k, gamma 1 k, all of them will depend on f delta naught and delta 1. So actually, these are nonlinear orthogonality conditions. Okay, so theta k, gamma naught k, gamma 1 k depend on f delta naught and delta 1. So so it's really a kind of nonlinear orthogonality condition. Okay, and if those are not satisfied, where your solution is not smooth, whatever the smoothness of the data. So generically, you have singularity. Okay? And this is what was rather unexpected for us. So now, in the remaining time, I'll try to explain why you have such singularities and what are their nature, why you have some orthogonality conditions and how they are related to possible singularities. And then I'll explain briefly how the proof works. So maybe the first step is to study the linear equation. Okay, so I will further simplify the model. And now what I will be looking at is just y dxu minus dyyu equals f, okay, with some boundary data. And so I'm still taking u on sigma I equals delta I. And I'm taking some homogeneous data. So u for y equals plus and minus 1 equals, okay, so I can always put 0 because it's just a matter of lifting the, I can put plus and minus 1, but then I just lift what I haven't. Okay, since I'm looking at a perturbation of y, this is enough. Okay, so this is typically the linear equation that that I want to look at in this first step, just to explain where these orthogonality conditions come from. So this is an equation that has been widely studied in many different contexts, actually. So it's studied, for instance, in kinetic theory, where it's called the Kolmogorov equation. So denoted by K in the following. And it has been studied a lot, at least in the PD community, in the 70s, so by Oleinik, and also by Fischera, by Pagani, so who were Italian, and in France by Bawendi and Griswald. So again, there was a lot of stuff that was known about this just linear PDE. And so the theorem, so here I'm gathering some results by Fischera, by Pagani, and by Bawendi and Griswald. that you have a nice well-posedness theory for this equation. And so typically, so here I won't write too many Sobolev spaces, but I'll just use L2. So L2 is okay for everybody. What? What, Sobolev space? Okay, so I assume that F belongs to L2 of omega. So this just means that the integral of F squared on omega dy is finite. Okay, and similarly, I assume that delta I and their y derivative belong to L2 of sigma I, which means that the integral over sigma I of delta I of y square plus its first derivative dy, this is finite. Okay, so those are the only assumptions on my data. And in that case, you can prove that there exists a unique solution of this equation. Okay. There exists a unique solution, U, and U. So it's a unique solution, and it's a little bit smooth, but not completely, not extremely smooth. So, so typically what you have is that dyyu is in L2, just like F, okay? So the idea is that if your source term is in L2, then each of those is also square integral. Each of those is in L2, okay? So dyyu is in L2, and y dxu is also in L2. So you see, it's not completely a classical solution, because here, this dxu is not integrable, okay? So dxu is not well defined. Well, it's not an L2 function everywhere. It's just when you add this weight, so you have a potential singularity, but when you add the weight, the singularity is somehow smoothed out, okay, close to y equals 0, and so you have something that belongs to L2, okay? So when you look at this theorem, so first so it's nice because you always have some well-posedness theory that you can use as a black box. So it's always nice. And the observation that you can make straight away is that the equation is stable by differentiation in x. Okay, because y does not depend on x. So if I apply dx to the equation, dxu satisfies exactly the same equation with a source term that will be dxf. And I can also identify the boundary data for dxu just by taking here you take the trace and you divide everything. So the observation is that dxu is a solution of the same equation with a source term that is dxf and boundary conditions that I will call delta I. So dxu on sigma I, this is equal to delta I, and delta I, so you take the trace of this equation on sigma I, and so you will have 1 over y f at xi y plus the second derivative of delta I. Okay, but so this is completely explicit in terms of the data, so it's nice. Okay, so let's assume that everyone again is smooth, compactly supported, and so on, so that you have. So what you want to do here is say, okay, well, I have a well-posedness theory for this equation. The equation is stable by differentiation in x. So if everybody is smooth, compactly supported, and so on, so that when I look at these iterates, they satisfy the assumptions of my theorem here, everything will work very well, like these two observations. Right? And this is false. Okay? So I don't know how to say this, the conjecture is that you can have, the conjecture would be that if you look at this, that dYy dxu is also integrable, and y dxxu is also square integrable. Okay, just when you apply you iterate the theory, and this is false. Okay, it's false because you typically need some orthogonality conditions, and this is what I will try to explain now. So the reason number one. So let's say the first way to look at things is to say, well, let's look at the equation. Say you look at a potential candidate for dxu. So you look at the solution v of your equation. So y dxv minus dyyv equals dxf, with v on sigma I equals delta I, and v at y equals plus and minus 1, which are equal to 0. Okay? So this one is a good candidate for dxu, right? Because this is exactly the equation that is satisfied by dxu. And so you want to check whether or not it's actually equal to dxu or not. Okay? And so if you say that this is a good candidate for dxu, well, you can integrate in x, and you find a solution that is, let's define this u tilde of x and y. So when you are in the upper half domain, you will integrate from x naught. Okay, and when you're on the lower half domain, you will integrate from x1. So it will be minus integral from x to x1 of v. Okay, so this one satisfies dxu tilde equals v. You can prove that it satisfies the correct equation in each upper half and lower half domain. So you have y dx u tilde minus dyyy u tilde equals f in omega intersected with y positive and in omega intersected with y negative. Okay, so you might think, okay, well, this u tilde is just u and I'm done. And it's not, because actually it might have a jump across the line u equals 0, because you define it in two different ways. Okay, you have your domain. This is the line y equals 0. When you're here, you integrate from this boundary. When you're here, you integrate from this boundary. And so you might have a jump across the boundary y equals 0. So in general, u tilde and dy u tilde have jumps across y equals 0. And so u tilde is different from u. And the only way to prevent them from having jumps is to assume that your data satisfies some orthogonality conditions. The orthogonality conditions are exactly here to prevent the jumps. Okay, and so you have orthogonality conditions. To prevent jumps. Okay, and so if you have these orthogonality conditions, and so if you don't have a jump, then things are fine, and u tilde is equal to u, and so you have some extra regularity on u. Okay, so that's the first way to look at things. Another way is to look at actually some potential singularities of your equation close to the points xi 0. So the reason number 2 is to look for singularities. So because in the sense of distributions, say dxu is still a solution of this equation. This is true. Okay, you are allowed to differentiate a linear equation in the sense of distributions. This is fine. Okay, if I'm talking Chinese, please interrupt me. But okay, so dxu is a solution of this equation. Okay, and you also have another solution, which is this V, which I defined thanks to the theorem that I just erased. And so if dxu is different from V, then this means that you have a kind of non-uniqueness for the equation, right? In a very weak space, a negative Sobolev space, something like that, but it means that you have non-uniqueness. And this is what happens, and this is linked to the singularities. So the one lemma that we proved is the following. So you take, so you look at what happens close to, say, x naught 0. And you take k in z arbitrary, so both positive and negative integers. You set, okay, so maybe one thing that I can say as well is that for this equation, you have a kind of scaling invariance. You can see on the equation that x, one derivative in x somehow counts like 3 derivatives in y. Because, okay, division by y is like taking one derivative. So one derivative in x is like 3 derivatives in y. So you set r, which is x minus x naught. So here it's just x minus x to the power 2/3 plus y squared. So this is the analog of, say, some polar coordinates adapted to the scaling invariance of the equation to the power 1/2. And t will be y over x minus x naught to the power 1/3. Okay, and I define uk of x and y to be something like r to the power 1/2 plus 3k times jk of t. Okay, and for any k, you can find a function jk that is smooth. So for all k, there exists some jk, which is again c infinity over r, and which has some limits. So jk at minus infinity is 1, jk at plus infinity is 0, such that this is the solution of your equation. That uk is the solution of the equation. Okay? Okay, and these are exactly your singularities. Okay? And for k, so then if you want to have a solution with the correct boundary conditions, you need to truncate them, and there are a solution of the equation with a 0 source term, okay, with f equals 0. Then you can truncate them, say, in an annulus close to x naught 0, and then you get a solution that has exactly the same singularity in the vicinity of your point x naught 0, but which has a source term now, which is c infinity, and so on. So okay, so this somehow explains why you are in big trouble to prove some well-posedness theorem with high regularity. Okay, and so typically for k equals -1, the solution that you get is in a very weak space, and this is the one that violates uniqueness in the weak spaces. Okay, and then what happens is that for general source terms, so in general, what happens is that you can write u as so u naught times some truncation. Okay, this chi naught is a truncation. I'm not writing it precisely, but you truncate your solution plus u naught tilde, which is the same one but close to x1. Okay, times some truncation k1 plus some regular part, and with some coefficients. Okay, so in general, if you have a very nice source term, again, what you can do is decompose your solution, so the one that was provided by my theorem previously, by Bawendi, Grisvard, and so on, Fischera. So you can decompose it as two singular profiles located and whose singularity is concentrated close to xi0 plus a smooth part. And so this is another way of seeing these orthogonality conditions. These orthogonality conditions are here to ensure that these two coefficients are 0. Okay, so it's another way to look at things. Okay, so my time is almost up. So so I hope I have convinced you that for this linear model, you have such orthogonality conditions and singularities, and now you have to go to the nonlinear case. And here I will be very brief because it's quite technical. So I'll just give you just the general scheme. And the idea is to have to solve the equation thanks to an iterative scheme. Okay, so you define a sequence UN which solve the following equation. So you have UN dx UN plus 1. So you assume that UN is known and constructed, that it's a smooth function in the vicinity of y. So, and you solve UN dx UN plus 1 minus dyy UN plus 1 equals some fn plus 1. And u at sigma I equals, say, some delta I n plus 1. U at plus y equals plus or minus 1 equals 0. Okay? So it's un plus 1, n plus 1. Okay, so you assume that un is constructed, and you construct un plus 1 in the following way. So from the point of view of un plus 1, this is a linear equation. It's very similar to the toy model that I just wrote. Okay, the only difference is that instead of y, here you have un. But everything I just said, you can extend it to linear equations with, say, arbitrary coefficients that are in the vicinity of y. So you need to extend that linear theory to more general transport equations like this, but this is manageable. Okay. So the first thing is to do that. You extend your theory to general linear equations. And then you see that at each step, you choose the data, so the fn plus 1 and these boundary conditions, so that the orthogonality conditions are satisfied, okay, at the linear level. And then you are able to construct un plus 1, which is smooth. Okay, so, and this is exactly how you do things. And then when you pass to the limit, as n goes to infinity, you get a solution of your original problem, and you inherit some nonlinear orthogonality conditions. And they are nonlinear because, obviously, at each step, the orthogonality conditions that you have will depend on un. So that's one of the complicated things about the scheme, that you change the orthogonality conditions at each single step. So you have to analyze how they depend on un and so on and so forth. So this, I'm putting everything under the rug. So it's just asking you to trust me. It's complicated, but it works. And this is how, in the end, you get some orthogonality conditions. So I'm done. Maybe just to conclude. So again, everything can be and has been extended to the Prandtl equation. So it's not specific to the toy model that I just wrote. The singularity is the same. Actually, really, this is this toy model is exactly the same, present as well in Prandtl. So it's same singularity, same type of conditions, and so on. What I think is that it's very unphysical, okay? Because the boundaries that you introduce at x0 and x1, they are not actual boundaries, okay? They are artificial. You are introducing them, so there is no reason why you should have such singularities in the vicinity of these 2 points, x0 0 and x1 0. So probably this is not the correct boundary condition, and you should replace it by, I guess, some kind of transparent boundary condition, but I have no idea what that would be. And so my question to you is whether you have encountered such things, say, in numerical simulations and so on, and how you bypass the probable singularity that you have. Do you have any idea what one should take as a boundary condition here in order to avoid these singularities, which again, insist, are not physical? Okay, so I'll stop here, and thank you for your attention. And sorry for going a bit over time. Yeah, I was told so. Yeah. I went a bit quickly because I was already going a bit over time. Okay, so several things. I didn't mention this because I'm not sure it is a community in which you are very familiar with it, but this is very similar to what happens when you look at elliptic equations in domains with corners, you know. And for instance, for elliptic equations in domains with corners, you have exactly the same phenomenon where you have some explicit singularity, which is in that case is just written in polar variables. So usually it's something like some power of r, where r is your actual radius, times a sine or a cosine or something like that. Okay. Of the angle. So in that case, I would say things are much easier. And so we tried. So we went to. This is something that we found afterwards. Okay, this is more or less the historical thing of how we went through things. But so we tried to kind of to find the singularities by kind of mimicking what we saw for elliptic equations in domains with corners, but respecting the scaling of the equation. So this is why this would be your angle or the tangent of the angle. Say if you just had some an elliptic equation and some usual polar coordinates, this would be the tangent of theta of the angle, and this would be your radius. But here, because of the scaling of the equation, because the scaling of x and the scaling of y is not the same, you have to tune carefully these powers. Okay, so and then it was a kind of trial and error thing to find the singularities. So we tried something like some power of r times g of t, and we tried until we found something that that led us to. So we performed some numerical simulations, and what we found was that if you choose carefully lambda, but again this is exactly the same. You have exactly the same thing for in domains with corners. If you tune lambda correctly, then you find a G which is smooth. So you choose your parameter lambda so that somehow you can. So G will be the solution of an ODE, okay? And then you say you can construct solutions of the ODE at plus infinity and minus infinity, and then you have to connect the two branches. And your lambda allows you, playing with lambda allows you to connect the two branches in a smooth way. So that's one way of looking at things. I don't know if that answers your question. Yes. No. I think it's completely unrelated. So because here the singularity. So let's say. I think it's really different because so what. Okay, so if I'm looking at so here you would have a Goldstein singularity. Okay, and the Goldstein singularity is at this point. So what you look at is the behavior of dyu. So this is the quantity that cancels at the separation point. You look at dyu at y equals 0. So you see, by definition of the separation point, this is the quantity that vanishes. And the Goldstein singularity is that it vanishes like x minus x star, or x star minus x rather, to the 1/2. Okay, so this would be x star. But here, so and then so you have your say this is the line where u equals 0. Okay, so here you have u negative and here you have u positive. here it's really a different phenomenon, I think. Yes. So yeah, I don't know. So I guess one good problem would be to look at things right after the Goldstein singularity. Okay, so you look at you rather look at something like that. Okay, so you still put, say, an arbitrary boundary here, which would be x equals x1, but now you take say you take x naught equals x star. Okay, so at some point with Nader-Mahmoudi, we started doing some computations, and then I think we stopped, but just because we were far apart from one another, and it didn't. So we tried to extend somehow the solution that we had for x lower than x star to x bigger than x star. I think one of the things that prevented me from doing that was the belief, and this also came maybe from discussions with UPI, that the Goldstein singularity was not physical, and that in any case, in that region, you should replace Prandtl by, say, the triple deck model. And so maybe I'm a bit lazy, but I didn't want to spend too much time on a mathematical problem which I knew was going to be hugely technical if afterwards, you're not rewarded by the fact that you did something that had some kind of physical relevance. So that's why we didn't go further into that, I guess. And so my understanding was that when you passed the singularity, then the Prandtl equation became valid again, and that's why we started looking at recirculation well past the singularity. But I'm not sure. So to answer your question, I'm not sure that you would get the same type of singularity if this dotted line arrives to your boundary. I don't know. Maybe it depends on the. So for sure, it depends on the way, I guess, this line starts from a. So no, you don't. Oh well, for the linear equation, you don't, and this is typically so in the weaker space, meaning negative Sobolev spaces. So no, at the linear level, you don't. So I expect that you don't have uniqueness at the nonlinear level because of these singular profiles. Because so maybe I can. So here, if you look at what happens here for k equal -1. So you have a very singular solution. Okay, it's not even in L2. It's really very, very weak. And so but you can truncate it somehow. Okay, so what I mean by that is x0, x1, and I multiply this by a function that is identically equal to 1 in a neighborhood of x0, 0, and that is supported like that in an annulus. So it's let's say a radial function, okay, so 1 close to x0, 0 and 0 elsewhere. And in that case, so let me call a small u sing -1. This one that I just truncated. And then this one is a solution of my problem. With a source term that just corresponds to the part that is truncated, okay? So you will have an f -1, say, and this one is really super smooth. It's C infinity. It has no singularity whatsoever. It's yes. Well, yes and no. So actually, I didn't write it, but here you also have compatibility conditions in corners, okay, for exactly the same reason. So this is classical for parabolic problems. So you have I didn't write them down, but you have some compatibility conditions in the upper and lower corners, like that. And it's clear that you can see these compatibility conditions as actually some orthogonality conditions. This is exactly what they are. You need some quantity to cancel, okay? Except that in that case, the quantity that needs to be cancelled is really the value of, say, a combination of your data at a given point, right? Whereas here, it's a more non-local phenomenon, because it's really the whole integral of your integral against a test function that has to vanish. So it's similar, but not completely so, because let me phrase this another way. Typically, compatibility conditions, if you take compactly supported data, they're always satisfied, right? Because everyone is zero close to the corners in which you need to have that compatibility condition. So you just check that 0 equals 0. So this means that you, from a functional analysis point of view, you can solve things with data in a space of codimension 0. Stop me if I'm talking Chinese here, but here you solve things with data in a space of codimension 2. And you have no choice. That's life. Okay, so being in a space of codimension 2 is really very restrictive. It means that generically the orthogonality condition is false, which is not, to me, it's not exactly the same as a compatibility condition, but it's similar in a way. No, I think it's general, because in the end, we have a necessary and sufficient condition. So we prove that if the orthogonality conditions are satisfied, then we are able to construct a solution with our scheme. But we also prove the converse. We prove that if a smooth solution exists, then the data, at least we didn't expect it at all. I mean, for a very long time, we tried to prove that that everything was well behaved. It was really a surprise when we tried and we couldn't, and we couldn't, and we couldn't, and at some point, when you try to prove something and you're not able to do it, you end up. Also, obviously, you question your own abilities, but you also question the validity of the point you're trying to make. And so then when you reverse that's how we okay. But actually there are some false statements in the literature. Okay. Yes. But again, I have questions for you. If you know what we should do, that I'm very interested in that. Thank you.